Today we are going to discuss the axial magnetic field of a solenoid. Now, first of all, let us draw the cross-sectional diagram of a solenoid. Suppose we have made the cross section of a solenoid. This is the axis of the solenoid, and this region is the core of the solenoid. This region is the coil of the solenoid, and this is the inside part of the solenoid. Now, suppose a point P is on the axis of the solenoid. This is the point P, which is situated on the axis of the solenoid. The radius of the solenoid is A, and the length of the solenoid is L. Okay. Now, take an element here. The thickness of the element is dz. Okay. From this end, the distance of this element is z, and distance of this point P from this end is z0. Okay. Now join these two points. Suppose this is angle theta and this is angle theta 2, and this angle is theta 1. Okay. Now let us derive the expression for the magnetic field due to this solenoid at this point P. First of all, we know from our previous discussion that the magnetic field due to a circular loop at some distant point is B is equal to mu 0 I a square by 2 into a square plus x square whole to the power 3 by 2, where this distance is x, the radius of the coil, radius of the loop is a, and I is the current passing through this loop, and we have derived the expression for the magnetic field at this point, at a distant point, say P, for a current carrying loop. Now we will use this expression of the magnetic field in this case of the solenoid. Now for this case, at the point P, the magnetic field due to this element will be this is previous case. Magnetic field due to the element of thickness dz at point P is dB is equal to mu 0 I is the current through this solenoid, A square by 2 into, look at here, this case for this for this special case, the distance here is actually this, which is z0 minus z. We will replace this z0 minus z in the place of x. So we can write a square plus z0 minus z whole square whole to the power 3 by 2. Now this is not the case of a single turn. Within this dz element there are several number of turns. Suppose the total number of turns of the solenoid is n. Therefore, within dz element, the number of turns will be, look, the total length is L, okay, and the for the entire length the number of turns is this n, okay, but we have to calculate the number of turns within this elementary area only this element. So the total number of turns within dz is n by L into dz. So we will replace here the single in the place of single number of turns or 1, we will replace this term in dz by L. Now rearranging this equation, mu 0 n I a square dz by 2L into a square plus z0 minus z whole square whole to the power 3 by 2. Okay, Now let us calculate few more terms. First of all, from this figure, look, A by z0 minus z is equal to tan theta. This is A, this length is this is actually the radius. A by z0 minus z, this length, is equal to tan theta. Just take its inverse, z0 minus z by A is equal to cot theta. Okay, therefore z0 minus z is equal to A cot theta, or minus dz is equal to minus A cosec square theta, or this minus will be cancelled out, and dz is equal to A, sorry, you can for this case there will be a d theta, A d theta by sine square theta. Now we have got the expression for this dz. Again, another part. A by root over of a square plus z0 minus z whole square is equal to sine theta, or a square plus z0 minus z whole square whole to the power half is equal to A by sine theta. Or a square plus z0 minus z whole square whole to the power 3 by 2 is equal to a cube by sine cube theta. Now replace these two in this equation. Okay, let us go to the next page. For our convenience, I am writing it another time. dV is equal to mu 0 n I a square dz by 2L into a square plus z0 minus z whole square whole to the power 3 by 2. Now replace this dz and this a square plus z0 minus z square whole to the power 3 by 2 term with our pre-derived expressions. Now this is mu 0 n I a square by 2L. For this dz we already have find out the expression a d theta by sine square theta. Now write down here a d theta by sine square theta into For this term, a square plus z0 minus z whole square whole to the 3 by 2 term, we have already find out a cube by sine cube theta. So write down here sine cube theta by a cube. Now by simplification we can write, look, this a square into a will be a cube, and this a cube can be cancelled out, this sine square theta term and this is sine cube theta term, only one sine theta term will survive. So we can write mu 0 n I by 2l sine theta d theta. Now again come back to the main figure. Look, this angle is theta 1. Which angle? From the first end of the solenoid to the point P. This is the angle theta 1, and at this end, the next end, this angle is theta 2. So for integration or if we want to calculate the total magnetic field, we have to take the integration of this dV, and we can write mu 0 n I by 2l integration sine theta d theta. Now we have to write the angle or integration limit. Here first of all we can write the angle is theta 1, or the lower integration limit is theta 1, and upper integration limit is pi minus theta 2. Therefore B is equal to mu 0 n I by 2l into cos theta 1 plus cos theta 2. Now if the solenoid is very long, then theta 1 will tend to 0. Similarly, theta 2 will also tending to 0. And we will get B is equal to mu 0 n I by 2l cos 0 plus cos 0 is equal to mu 0 n I by 2l cos 0 1. So 1 plus 1 means 2 into 2 is equal to mu 0 n I by L. This expression is similar to the expression which we have derived already for the case of Ampere's law, or we have derived previously the expression for magnetic field due to a solenoid using Ampere's circuital law, and the result was same as this. Thank you.